would be very surprised if you didn't have questions. In fact, I'd be concerned if you didn't have questions.
Yeah.
Okay, so we are rolling here on our lecture, January 28th, 2016. We are talking about quantum systems and boundary conditions. And I want to start a little bit with boundary conditions. So, it turns out there are several types. For example, in particle in a box, we have the wave function needs to go to 0 at box boundaries. And in the harmonic oscillator, the wave function needs to go to 0 as x goes to infinity. And what we're saying there is you can't stretch the oscillator out forever and ever and ever. The wave function's going to die out. That spring is going to require more and more potential energy, and at a certain point you just have very low probability of fighting the particle out that far.
So it's saying it's going to 0 as x goes to infinity?
Let's see, yeah, so I forgot the 0, didn't I? There it is, 0 as x goes to infinity. But we're going to encounter a new type of boundary condition today. And in our lab period, actually, earlier in the week, we were looking at these cyclic polyenes, and we saw some interesting things with treating those as approximations to particle in a ring. So we want to talk about the unique boundary conditions that we'll find with particle on a ring. Let's use the angle phi. This is the so-called cyclic boundary condition. And the way it arises is you're saying, hey, the wave function is around a ring described by the angle phi in the chosen coordinate system. We're going around the ring. And if that's true, if you're at a certain point in the ring and you go completely around again, another 2 pi radians, just mathematically and physically, if you cycle around once, it better be exactly where it was before. And that's called a cyclic boundary condition. So these are linear boundary conditions, particle in a box, harmonic oscillator. They make sense to us. The cyclic one should also, you just can't augment it by 2 pi and have it be different from what it was. Okay, and more generally, yeah, you could probably say in pi. So let's trace the whole genesis of particle on a ring cyclic boundary conditions. And to do that, we are going to find particle in a ring quantum mechanics. So let's open up the chapter and get on to particle on a ring. Now, as always, we start with the Hamiltonian, and we'll start in this case with a coordinate system around which we are going to build particle in a ring conditions. So we have in 3 dimensions our I, J, and K Cartesian unit vectors, and we are going to define a ring in the XY plane of radius r, and there's the angular coordinate phi, counterclockwise from the x-axis. Remember, I is x, j is y, and k is z. So our particle is somewhere along this ring of radius r. And again, our book gives a very nice figure. It's figure 827 that shows this exact situation. All right. And I guess I only have a couple colors. Oh, I have some more colors here. So let me just remind us that the ring radius is r, and in this case, it's going to be fixed. Now, what is the Hamiltonian? We can start with spherical polar coordinates and realize that if we're constrained to the xy plane, theta is fixed at pi over 2 radians. And we already said that this radial distance is also fixed. So our Hamiltonian, in actual fact, is only a function of this phi coordinate.
And why is theta fixed?
Because it's in spherical polar coordinates, theta is an angle down from the z-axis. And to put it in the xy plane, that theta has to be slammed down to 90 degrees. Good question.
So r and theta is fixed.
So r and theta are fixed. The only thing you get is the ring. Fixed radius, ring in the xy plane. Okay? Now, what does this Hamiltonian look like? And we are given it actually as equation 839 in our text. And it looks like this. Hold on just a second while I get all. So you have a second partial derivative with respect to r squared plus 1 over r ddr plus 1 over r squared d squared d phi squared. Now, there's 3 terms in that function, that operator. Which ones go away?
R?
Anything that involves an r derivative goes away, doesn't it? Because we have a fixed radius. And we haven't even shown the theta derivatives. They go away too. So our complete particle on a ring Hamiltonian is 1 over r squared, where r is treated as a constant. Okay. If we have one-dimensional Hamiltonian, okay, and by the way, there's another implicit assumption here that we should mention, and that is the potential energy operator is 0 on the ring. So if we wanted to kind of talk about the potential energy operator, V of r, theta, and phi, the potential is infinite if theta is unequal to pi over 2 radians. And it's infinite if let's see, if r is, if the actual radius is unequal to r, the potential's infinite, and the potential is 0 when theta equals pi over 2 and r equals r actual.
Wait, so we're crossing out potential though, right?
In other words, if you're off the ring, either because you're not in the xy plane, that's theta, or you're not at if your actual thing is not at the fixed radius r of the circle, your potential is infinite. However, if you're on the ring in the xy plane, your potential is 0. It's the cyclic equivalent of particle in a box. Okay?
And what is the equation for the Hamiltonian come from?
Okay, now, this, there are, let's go back. I appreciate the question very much. Let's go back, I believe, into the last chapter, and we are given the Hamiltonian in various curvilinear coordinate systems. So let me find that section, and it's worth it to bring it out. And there are some very standard calculus 3 kind of stuff that allows you to do it.
Different forms the Hamiltonian can take on?
Look at table 7.1 on page 261.
Okay.
They give you the Laplacian, the operator in spherical polar and Cartesian coordinates, and you can convince yourself from table 7.1, page 261. So basically, see table 7.1, page 261 for how did we get all these radial terms. Okay. Now, so basically, while we're on the ring, here's the important thing: we're only going to consider the kinetic energy, the rotational kinetic energy of going around the ring. Okay. Now, it's time to do the Hamiltonian. And to get Schrodinger's equation, so we basically are going to have h of phi psi m sub l of phi equals e m sub l psi m sub l of phi. Let's just make no secret about it that m sub l is going to be an angular quantum number about the z-axis. And it's completely analogous to the m sub l you learned in chemistry classes. That's called the magnetic quantum number. And it comes from this type of problem. Okay? Now, we know what this is. And by the way, let's make a little correction in my expression. I forgot something that's actually quite important. What is missing? If that's a Hamiltonian, there's something missing there, and it can't be missed. It's really important. What did I not do? I left out a factor in front of this.
H bar?
Yeah, I need a minus h bar squared over 2m out in front of all those derivatives. Okay, so now let's put that in. I need minus h bar squared over 2m r squared. So that's the pre-multiplying factors, then d squared d phi squared, and it's psi m sub L of phi equals E m sub L psi m sub L of phi. That is what the whole problem reduces down to. In our lab earlier in the week, we kind of used the results of this quantum mechanics. We got this beautiful straight line, just absolutely lovely. So we now need to solve this equation. Now, given our assumptions, all of this is just a constant. If these are electrons, it's the mass of electron, whatever the R is and whatever h bar squared is. Now, we see the second derivative of the function equals the function. Let's say at times some constants. We've seen this before, haven't we? But the second derivative in this case is with respect to phi. So we take the second derivative, and there are two classes of functions that should immediately come to mind. And what are they?
So sine and cosine.
Sine and cosine.
And
E to the kx, e to the minus I kx. Okay? So, in principle, we can do either one. I am just, for reasons that will become clear, I'm going to choose the complex exponential form to do this, okay? So I'm going to say psi m sub L of phi is of the form a e to the I kx Okay. So, in fact, let's just we'll get the different sign that way. Okay. So let's assume the wave function is of this form, and we'll find out what the constant k is, and we'll find out what the constant a, the normalization constant, is. So if I assume this and actually put it in both sides, what do I get? I get minus h bar squared over 2mr squared. That's our constant. Now I take two derivatives of this function, and I'll write what comes out from the derivatives. I bring out ik twice, right? So that's I squared k squared, and then and I'm just left with a e to the I kx. And this equals E m sub L a e to the I kx. Okay, well, you can see immediately what happens. That I can cancel this out with this, and I'm left with the result that the energy levels E m sub L are of the form, and now I squared is what? Negative 1 times minus h bar squared, so it's h bar squared over 2mr squared k squared. No boundary conditions yet, though. Okay,
So EML equals.
all of that.
All
And this M is a mass,
Mhm.
and this is a quantum number. We're gonna
You don't know.
see what's going on in just a second. Okay. Let's erase all this. Okay. Now we invoke the cyclic boundary condition. Okay. Okay. Now, let's figure out what this thing does at various points in the circle. Okay? What does it do? And e to the I k phi equals cosine phi plus I sine phi. This is the Euler relation. Okay. Well,
So what are we doing now? Sorry.
we're invoking the cyclic condition.
Okay. So we're steering away from particle on a ring now.
Oh, this is particle on a ring.
Okay, we're still doing it. I'm sorry, I thought it ended right here.
No. I mean,
Is this
this is just a continuation.
Okay.
We figured out what K has to be, to make this all work.
Yep.
But now we're saying, hey, e to the I k phi
Mm-hmm.
plus m sub l phi has to be e to the I k phi. In other words, and we'll let m sub l equal 0. 1, 2, 3. And we can even put plus or minuses on there. Now, isn't it true Okay. Isn't it true we can break a power up into two separate terms?
Yeah.
So that's what this really means. Okay. And notice this comes out, and that says what am I doing wrong?
So e to the ik phi plus m l
What am I
phi.
doing wrong here? Hold on just a second. Doesn't help. I kind of messed up here. Hold on.
Okay.
Okay. A cyclic boundary condition says e to the ik phi equals e to the ik phi plus e to the ik phi plus n or m sub l phi. There we go. Where m sub l takes on these values. Okay. So this is the cyclic boundary condition. And let's take it just a minute to review what it says and why it's right, okay? We're saying for this wave function to go all the way around and have the same value when you've got around 2 radians, e to the ik phi has to equal e to the ik phi plus m sub l phi, where m sub l has integer values.
Okay. I don't understand how that equals it though.
Okay, now, okay, what this says, so this says e to the ik phi equals e to the ik phi e to the ik m sub l phi. Okay, now we had a little difficulty as I kind of sorted through some misconceptions, but now we've kind of worked it all out. We know what's going on, and we want to apply the cyclic boundary condition. And what we want to do is kind of specialize on the simplest case, and that is for a cyclic boundary condition in a circular motion problem, like a particle on a ring at constant radius, the wave function at angle phi has to equal the wave function at phi plus 360 degrees, or 2 pi radians. That's what the boundary condition means. You can't circle around and end up in a different place on the wave function than where you started. So that's what we're saying. It's a symmetry constraint, if you will. It says the thing has to come back to itself. Okay, this is going to be our final answer. And we'll get that, what that normalization constant A is in just a minute. But it'll be I m sub l of phi, where m sub l takes on the value 0, plus or minus 1, plus or minus 2, and so forth. But we have to prove that. And here's how we do it. We have realized that the wave function psi of phi has to equal the wave function psi of phi primed, where phi primed is phi plus 2 pi. And that's just another statement of the cyclic boundary condition we have on the left part of the board. Now when we put in the general form for the wave function, ae to the ik phi, the cyclic boundary condition says, hey, that's got to be equal to ae to the I phi primed, where phi primed is phi plus a full 2 pi radians or 360 degrees. That is how we implement the condition. Now, when we do that, the constants A cancel out from the blue boxed expression as we go into the red boxed expression. The e to the ik's cancel out, and we get the number 1 equals e to the ik times 2 pi. Now, we'll use the Euler relation between the complex exponentials, the cosine and the sine, to say our cyclic boundary condition is 1 equals e to the ik 2 pi. But that's equivalent to saying 1 equals cosine of 2 pi k plus sine of 2 pi k. And if that's going to equal 1, the cosine is going to have to equal 1, and the sine is going to have to equal 0. And we're going to look for an angle where that is true. It is only true if what's in that cosine or the sine, if 2 pi k equals an integer times 2 pi or 360 degrees. If that's true, then we have the conditions, the 2 pi's cancel out, that this k term has to equal the integer m sub l. And convince yourself that m sub l can take on the values, any integer values, positive or negative. And that's what leads us to this wave function psi m sub l of phi equals a e to the I m sub l of phi. So we've now proved, invoking the cyclic boundary condition, that this is what the wave function must look like. Let's now normalize this wave function, and we'll extract the quantum energies in just a moment. So to normalize the wave function, we say that psi m sub l star of phi, psi m sub l of phi times d phi, phi being an integral from 0 to 2 pi radians, we say that that has to equal 1. But given the forms that we have to deal with, phi equals 0 to 2 pi, and now we have a e to the I m sub l of phi star times a e to the I m sub l of phi d phi. Now, here's a good place to remember what the complex conjugate is. In a complex conjugate, what do you replace I with?
Negative I.
Okay, so we have the result we could pull the a squared out. It's a constant. We have e to the minus I m sub l of phi times e to the plus I m sub l of phi d phi. All of that has to equal 1. Now, notice that e to the minus m sub l phi, I to the minus I m sub l phi, and e to the plus I m sub l of phi, these are equal and opposite. They cancel one another out. And we get the very pleasing result that all of this boils down to a squared d phi between 0 and 2 pi. radians. Let me remind you here in this one, there's a 2 pi. But this is nothing more than a squared phi evaluated between 2 pi and 0. And this is just a squared times 2 pi. So our normalization condition then becomes 1 equals a squared times 2 pi, or 1 over 2 pi equals our normalization constant squared, or 1 over the square root of 2 pi equals our constant A. So now we literally have it all for particle on a ring. We have every last bit of it. We have the Hamiltonian, we have the potential, we have the wave functions, we have the quantum numbers, we have the boundary conditions, we have the quantum energy levels. We have it all. Every last bit of it. Okay? Now, let's
Where
go.
did the E's go? Oh, they just canceled out just from the, yeah.
Where did what go?
Nothing.
Okay. Oh, I erased the energies. I didn't mean to do that. We'll take those up from your notes, okay? So, let's summarize what we found for particle on a ring. Just another thing, a ring. Santa baby. You know that song?
Yep.
It's one of my favorites. It would be, wouldn't it, right? Okay. So, particle on a ring, our Hamiltonian, so we'll do strictly on the ring. So, on the ring, what is the Hamiltonian?
Negative h bar squared over 2mr squared.
Second derivative with respect to phi, okay. Our wave functions are the form psi m sub l of phi, and they are 1 over the square root of 2 pi e to the I m sub l phi, and m sub l can take on the value of 0, plus or minus 1, plus or minus 2, and so forth.
We left out V just because it's not involved, right?
Right. So let's just note that there's no, when we're on the ring, which we're going to be, there's no potential energy. Okay? So, now look back in your notes at what we've written for K, and let's invoke that.
I'm gonna get to work, just wanna let you know I'm here.
Okay, I'll come by. We'll be through in 6 or 7 minutes. I took a look at it, and boy, you've really cleaned it up.
I tried.
Okay, so E equals h bar squared k squared
Okay, so it's really h bar squared m sub l squared.
over 2mr squared.
Okay, and the m sub l values apply equally well to
Okay, cool.
this problem. Okay, so with our lowest value of m sub l being 0, what's the rotational energy?
0.
0. I mean, and then notice the very pleasing result that m sub l comes in as the square, we don't care whether we get kinetic energy rotating clockwise or counterclockwise, they should be the same, right? And we get that. Okay?
So it should be 0.
So the 0 should be here. And by the way, do we have that problem that we had with particle in a box with the first quantum number going, with the wave function going to 0?
Not with this.
Not with this, that's right. So we can keep the 0 in this case, but we couldn't in particle in a box. Okay, so we've got the whole particle in a ring derivation right there, the results that have come from that derivation. Now, let's quickly consider how a plot of the quantum energies would look on a vertical axis. So, energy is going like this. So the energy is 0 right here. Then let's say this is m sub L equals 1. And, oh, I need more room. I'll say m sub L equals 1 right here. And then m sub L equals 2. And m sub L equals 3. Do you see what's happening with the energy levels? They're going up quadratically with the m sub L quantum number. So they're,
And so, yeah, I always thought it was the opposite.
it depends.
What we're talking about.
It depends on what you're talking about.
Yeah.
So as the rotational quantum number, the rotational angular momentum quantum number, it turns out.
Rotational quantum.
So this is the rotational quantum number.
Yep.
And as you get higher values of m sub L, your energy levels are lumping up quadratically, so they're getting bigger and bigger and bigger apart. Okay? So today we have really come a long way in specifying how the boundary conditions arise and what the consequences of those boundary conditions are. The cyclic boundary conditions say that this k value that we started with has to equal an integer m sub L, and the integer can be 0 or positive or negative. And again, we don't care whether it's positive or negative, you get the same energy since m sub L is coming in as the square. So this is a very lovely result. And in your take-home test,
This is involved.
you will combine this with particle in a box. So basically the xy plane you'll do in cylindrical coordinates, and the z-axis you'll do in Cartesian coordinates. All right.
And then you combine the degrees.
And you combine, and you, since there's no potential other than being it'll be the energy of the particle in a box plus the energy of the particle in a ring, and you'll specify the quantum state with two quantum numbers, a ring quantum number m sub L and a particle in a box quantum number n sub z. Okay, so you may be starting to see how to put these things together. So we're right at the end of our hour. Let's stop right here. This is a